Well, as you probably will not be surprised at all, since chemistry does tend to involve an awful lot of math, we can definitely do a lot of math with reaction rates. Now, the first thing I actually want to do here is to do a little bit of review on exponents. And so if what I review completely goes over your head, you'll probably need to go pull out your algebra book and review this and make sure that you understand these concepts, okay? Most of the time, if we do something like a 3 squared, most students are going to know, oh yeah, that's 9. They know a 2 squared is equal to 4. They know a 4 squared is equal to 16, okay? So squaring something doesn't seem to normally be too difficult. If I have a first power, what that means is that it's just whatever this thing is. So 2 to the first power is 2. A 3 to the first power is 3. 4 to the first power is 4. It's just itself. In fact, you probably know that if you're writing variables in equations and you just write an x, it's the same as x to the first power, just that normally we don't write that 1 up there. Normally we leave it off so that things don't get so cluttered and messy. The one thing that tends to throw students a little bit is when I talk about a 0 power. And so the thing that you need to remember is that anything to the 0 power is equivalent to 1. So 2 to the 0 is 1, 3 to the 0 power is 1, 4 to the 0 power is 1. No matter what you raise to the 0 power, it's always 1. So I wanted to review that and make sure that that was fresh in your mind before we get into this, because we will be talking about first and second powers as well as the 0 power in our rate equations. All right, now when we talk about a reaction rate, what is true is that the equation for the reaction has nothing to do with how I write the rate equation, okay? So let's assume that I'm talking about just a very generic reaction here, where I have reactant A reacting with reactant B to make product C and product D. The little letters are simply the coefficients in the equation, the numbers that you put in front in order to balance them, okay? So the reaction rate, and we have defined this before as the change in concentration per time. We can calculate that actual reaction rate. Every reaction rate has what's called a rate constant. This reaction constant, again, as we're going to learn a little bit later, is dependent on temperature and some other things. So it's going to vary for each specific reaction that you talk about. So this is the rate constant for the reaction, and you multiply that times the concentration of reactant A raised to some power times the concentration of reactant B raised to some power. Okay, this X and this Y are called orders. And you'll notice that I used X and Y. I did not use A and B because the reaction orders have nothing to do with the stoichiometric coefficients. Now, they may be the same, but if they happen to be the same, it has nothing to do with the fact that those also are the coefficients. It's just more of a coincidence that that's what the reaction order is. Okay? Rate constants and rate orders always have to be determined by experiment. There's no way to look at the reaction for an equation or the equation for a reaction and determine what the orders and the rate constant are. Now, sometimes you're going to be asked what the overall order for a reaction is, and if you're asked for that, all you have to do is add the X and the Y together. So if this is a 2, we say that reactant A is second order. If this happens to be a 1, we say that the reaction is first order with respect to reactant B. They can be a 0. In that case, we would say that particular reactant is at the 0th order. Okay, and so all I have to do is add the orders together. So if this is a 2 and this is a 1, the overall order for this reaction would be 3. Just a very simple sum. Okay, One thing that he does ask you to do in this section is to calculate, to figure out what the units on the rate constant are. And they are not always the same. They will change, and they change depending on what these orders are. So let me show you what I mean by that. You know that the reaction rate is expressed in molarity per second. The rate constant has units which vary on it. So let's say that reactant A is second order, so that means that that one would be squared. And let's also say that reactant B is first order, so that would be a 1 up there. Now remember, we don't normally have to put that 1 there. I'm putting it there mainly for the sake of example. You don't normally have to write that. So in order to figure out what the units on this K would be, I'm going to divide both sides by molarity cubed so that I can cancel these units out. So now what I'm going to have is rate constants on this. This molarity will cancel out with two of those molarities, or sorry, with one of these molarities, leaving me 2 behind. So therefore, the units on my rate constant are going to be 1 over molarity squared seconds. Okay? Let's say, again, for the sake of example, that in this particular case, maybe my X is a 1, but maybe the reaction order for reactant B is a 0. Well, if that's a 0, then this whole thing just goes to 1, and so the units aren't going to make a difference anymore. So I have molarity on this side, I have molarity per second on this side. I'm going to divide both sides by molarity. So in this case, my reaction constant is going to have units of 1 over seconds because both of the molarities will cancel out. Okay, we're going to do a whole lot more with the mathematics of reaction orders in the next video, but this one will get you started to at least determine what the units are on your reaction constants.